All right, today we are circling back to parent functions, and we want to talk about domain and range. So first up, I'm saying write the solution region that is graphed. So I can see an inequality. I can see that my solution region would be 4 or anything to the left, anything below it. So I think it's good to have the habit of seeing what the two extremes are. Our two extremes are the infinities. I have negative infinity to positive infinity. Okay, that really helps when we get into the interval notation. So we can look at our solution region in two ways. We can look at it as an inequality, so in inequality form, or using interval notation. We usually start you off in inequality form, and then gradually we wean you off of that and we move into interval notation. So inequality form here, well, we would say whatever our variable is of choice, usually x is less than or equal to 4. X is less than or equal to 4. So that would be the inequality form. Okay, but as interval notation, we show it as sandwiched in between two numbers, two extremes. So we're going to say, okay, it can be anything from negative infinity to positive 4, and it's inclusive. Now, infinity, whether it's positive or negative, right, it's a concept. It's the biggest or the smallest number you can possibly imagine. So whenever we write it, we always give it a parenthesis, because we're never going to be completely equal to that extreme. So we're reading it as anything from negative infinity up to positive 4. Now 4 can be part of our solution, so we give it a hard bracket right there. So we're saying when I read this back, x, our solution, can be anything that's more than negative infinity, because we can't ever be exactly negative infinity. It takes that little soft bracket or parenthesis up to 4, and it can be equal to 4. So we give it a hard bracket over here because it can be equal to 4 exactly. So anything that's in between. All right, looking at B, we want to do the same thing. So we're saying, okay, look at what's graphed. How can we write the solution region? Well, in inequality form, we're saying, well, x has to be greater than or equal to negative 3, but at the same time, it has to be less than 10, because I see it solid here and I see it hollow over here. So I'm going to say, okay, x is in between. I'm going to start off like that. So here I'm showing x is greater than, x is less than. X is greater than negative 3, and at the same time it's less than 10. Now one more thing I have to add. It can be equal to negative 3, but not to 10. So that negative 3 needs a little dash underneath it, just like so. So it's reading now back as x is greater than or equal to negative 3, and at the same time, it has to be less than 10. Boxed. So what would that look like in interval notation instead? So we're saying, okay, what are the extremes? The extremes are negative 3 to 10. It can be equal to negative 3, so it gets that hard bracket right there. But it cannot be equal to 10, so it gets a soft bracket or parenthesis over here. Okay, when I read that back, that's telling me that my solution region has to be more than negative 3, but could be equal to it, and at the same time has to be less than 10. It cannot be equal to 10. All right, next up, I'm going to zoom in a little bit tighter so we can see each graph. And what I want to do for each of these is I want to identify it. These are the same parent functions that we graphed last class. So I'm really going in reverse, and I'm adding in domain and range. So domain is the spread of values that x can take, and range is the spread of values that y can take. And we can write those in inequality form. We can write those in interval notation. We have some options here. So I'll show you both ways just for the sake of practice. All right, so here looking at the first one. So first is just identifying, well, what kind of function is this? We should recognize that this is exponential. So it is our exponential function with a base of 2, which just means that it's doubling from stage to stage. So the y value here is 1/4, 1/2, 1, 2, 4. Next would be 8. It is doubling from stage to stage. So I could write this as y equals 2 to the x. That would be the function itself. I could write it as f of x or g of x equals, that would be fine too. I'm just keeping it simple. All right, domain, what can x be? Well, if I trace my function, I'm seeing that it can keep growing from left to right. I could input any number in here for x. It could be negative 10,000, it could be positive 10,000, or anything in between, or less than, more than those numbers. So really, x can be anything. We say that as all real numbers. Another way we could write that in interval notation is saying, well, it could be from negative to positive infinity. Negative to positive infinity. So if it helps to add that to your picture, look at it like those two extremes. It could be anything from that span. Okay, range, we're now looking at the y values. So what can y be? Well, no matter what I plug in for x, it's going to give me a y value that is above where this asymptote is at y equals 0. So I can see that right here when I look at the y's, has to be more than 0, but has to be less than positive infinity. So I could write that two different ways. I can write that as, well, y has to be greater than 0. I could write it like that. Or I could say from 0 to infinity in parentheses, because y has to be more than 0, can't be equal to 0, and at the same time, it has to be less than infinity, right? The biggest number we can possibly imagine. All right, next one. What kind of function is this? Well, this is our square root function. So y equals the square root of x. Again, I could have written that as f of x, g of x, h of x, q of x. It doesn't matter. It's just easiest to write it as y equals. All right, I can see that because if I plug in a 0 for x, I get a 0 for y. If I plug in a 1 for x, I get a 1 for y. If I plug in a 4 for x, I get a 2 for y, right? They're all those perfect squares. So if I input a 9, I get out a 3. So square root function. So what can x be? Well, let's block out of view what it can't be, right? It can't be anything over here. So x can be 0 or more. Easiest way to write that is x is greater than or equal to 0. Let's say that I want to use my interval notation instead, right? There's my 0, and here is infinity, right? It's the other extreme. So x can be, it can be 0, so it can be anywhere from 0 to infinity. It can equal 0. It can never equal exactly infinity, right? It's an idea. It's a concept. It's the biggest number you can possibly imagine. All right, range, we're looking at the y's. So what can y be? Well, it can't be anything down here. So it has to be 0 at the smallest up to infinity, right? So y has to be greater than or equal to 0 or 0 to infinity. That's your other notation option. All right, next up, here we see, oh, that's the big V. What's the big V? Well, the big V, we're looking at absolute value. So absolute value would be y equals absolute value of x, like that. So here is my absolute value function. Well, what can x be? What's my domain? Well, it keeps growing from left to right. I can plug in anything in here for x. So my domain is all real numbers. Or I could say those two extremes from negative to positive infinity. How about the range? What can y be? Well, it can't be anything down here. Right here it's something real big and then it's getting smaller till it hits 0, then it's getting bigger again. So y has to be greater than or equal to 0. Or 0 to infinity, it can be 0, but never infinity. Okay, next one. So here I see my sideways s. I can see that when I put in a 1, I get a 1. Put in a 2, I get an 8. Those are cubes. I notice a cubic pattern. This is a cubic function. So y equals x to the third power. Okay, so what can x be? Well, it can be anything. It keeps growing from left to right. I can plug in anything for x right here. So all real numbers, or negative to positive infinity. Well, how about the range? How about the y values? Well, it keeps growing up and down, so all real numbers again. This is what's nice about the cubic function. The domain and range are both all real numbers, or negative to positive infinity. All right, down here, 5, we see that U shape. So that U shape should trigger for us, oh, it's quadratic. It graphs as a parabola. It's a quadratic function. So y equals x to the second power. Okay, so how can I tell that? Well, if I plug in a 0, 0 squared is 0. If I plug in a 1, 1 squared is 1, so is negative 1. In parentheses squared, it's going to get us 1. If I plug in a 2, I get a 4. 2 squared is 4. Negative 2 in parentheses squared is also 4. So again, quadratic function. When I plug in and I square, I get my output for y. So what can my domain be? Well, I see that it keeps growing from left to right. So those could be my infinities or all real numbers, right? Anything can plug in for the x. So all real would be fine, or negative to positive infinity, right? That would be fine also. How about my range? What can y be? Well, it can't be anything down below here, right? Can't be anything here. I see it's something big, comes down, hits 0, and then gets big again. So y has to be greater than or equal to 0. Or 0 to infinity. It can be 0, so it gets that hard bracket on the 0. Okay, last one here, the most complicated. We see the two asymptotes right here and here. This is our rational function. We also think of it as a reciprocal function. I'm going to write it as rational. We don't need two words to remember. So rational. So that is when we see 1 over x. We see a variable in the bottom. So here we see that as I move away from the origin, as I go over 1, I go up 1 over 1. As I go over 2, I go up 1 over 2. As I go over 3, I go up 1 over 3, and so forth. So I can see that pattern. Well, what's my domain? Well, x can be anything here or here. It can be really anything except for where I have this asymptote at 0. I can't ever have 0 because I can't have 0 on the bottom of a fraction. It's undefined. So I could write this as, well, all real numbers, just not 0. I can write it like that. Or I could say, well, it could be anything from negative infinity up to 0, union with, or 0 to infinity. So really, this notation is a more complicated way of saying anything but 0, right? It's saying, well, we'll count everything, just not exactly 0. Okay, what about the range? What can y be? Well, y has any value down here in negative territory, anything up here in positive territory. But the issue is that I have another asymptote at y equals 0, right? Because I can't ever get y to equal 0 if I have 1 in the numerator position. There is no value that I can plug in for x that would give me a 0 over here. So another asymptote. So y can be anything, all real numbers, just not 0. Okay, and then the more complicated way of saying the same thing is, well, could be negative infinity to 0, union with, or 0 to infinity, just like that. All right, so good review of just inequality versus interval notation. Looking at our parent functions in reverse, right? So given a graph, can you identify the actual equation for each function? And then can we add in what the domain and range values are? So domain, all the values that x can take. Range, all the values that y can take. Have a good rest of your day.